All right, I want to have a quick conversation about radicals and roots, just to make sure we're all on the same page about some of these super important ideas. So let's look at our classic square root of 20, for example. All right, first let's just sort of break down the pieces that we have here. We all know this shape, right? We know and love this guy. What's the name of that shape? Yeah, that's right. That's the radical symbol, right? And we use the radical symbol in order to write roots of things. And we'll talk about what that means in a second. There are two other numbers here. I know you're going, no, Mr. Ranking, there's one other number, but there are actually two. One of them is this guy in here, the guy inside the radical. And I love the word for this thing, so that's why I like to share it so much. The name for that word, or that number, the 20 in this case, is the radicand. Now there's another number here that we don't actually see, and it's hiding up here. If this is the square root, it's the second root of 20 that we're looking for. That number up there, which we sometimes don't write when it's 2, is called the index of the root. All right, so now that we have some basic definitions here, let's talk about first the thing that we never, ever, 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 ever want to hear you say or think about or anything like that. You may have had a teacher who was not real great in the past who told you something like this. Oh, well, go ahead, students. You can do your factor tree, and then if you have two things in your factor tree and they're the same, then they can go outside the radical. If we ever hear you thinking about this like that, we might just lose our brains. It's not math. It leads to wrong mistakes. It's purely procedural, and it's bad. So how should we think about that? We'll get back to that conversation in a second. First, we need to make sure that we understand what this means. So let's talk about our other operation. What is this doing for us? Why do we need to have the radical? We've got some other operations that we've talked about this year, right? We've talked about absolute value sum, and absolute value gives us a way to describe and to talk about the size of something, right? We know our old friend addition lets us sort of something, lets us essentially count and then put counts together, that kind of deal. We've got this idea of multiplication being counting by groups, sort of. And then we've got these exponents where it's like having groups of multiplications, right? We have something to the something power. We've got groups of groups. There are some operations that go with these, right? We talk about addition and subtraction being inverse of each other. We talk about multiplication, division. For example, one of the ways we could talk about 56 divided by 8 we know is 7. One of the ways that we could talk about that is we know that 8 times 7 is 56. So there's this relationship between multiplication and division where we can kind of use them to talk about each other. The reason why 8 times 7 is 56 is because 56 divided by 8 is 7, or we could say the reason why 56 divided by 8 is 7 is because 8 times 7 is 56. There's a 7 out there that you guys can't see off screen. So what roots give us an ability to do is talk about the same sort of relationship but for exponents. So for example, when we talk about the third root of 8 being 2, one of the ways we could talk about that is it's because 2 to the third power is 8. So exponents sort of give us the other, or roots give us sort of the other side of this exponent relationship, right? Because 2 to the third power is 8. And that's really the key to the definition of what a root, or what we're writing here with these radicals. That's the definition of what it is. It's the square root of 20. The second root of 20 is a number. It's just a number. And what's important about that number is it's the number that if you had two factors of that number. So if you had 2 copies of the square root of 20, right? What this number is it's the thing that if you had 2 copies of it, you would get exactly 20 when you multiply those together, right? So the same idea, like if we had the third root of 20, right? And someone said, well, what is that number? What that number is it's whatever number you'd have to have where if you had exactly 3 factors of that number, you would get exactly 20, right? So now, what are we doing with this factor tree? And why did Mr. Ranking yell at you about saying that you can't just say that you've got 2 of them, so you're going to have 2 on the outside? I want us to understand why that's happening. So really what we're saying with this factor tree is not just that this is the same thing as 2 times 2 times 5. What we're saying is that the square root of 20 is the same thing, and this is sometimes not true for negative numbers, so we'll worry about that later. But what we're saying here is the square root of 20 is the same thing as the square root of 2 times the square root of 2 times the square root of 5. And then when we look at simplifying this, what is the square root of 2 times the square root of 2? Well, remember, these things are of index 2, all three of these things. The definition of what the second root of 2 is that it's the thing that if you have 2 of that factor, you have exactly 2. So this is just 2 times the second root of 5, which we would usually just write as 2 root 5. But the reason why this 2 ends up not inside of a radical here is, well, it's, first thing, this 2 is not this 2. Right? What we're saying here is that because we have 2 factors of that root, we know we get that thing back. Why does this matter? Well, let's say you have the second root or the square root of 335. And you have that being multiplied by the second root of 335. Right? Now, we could do 335 times 335 and then take the square root of that. Or we could think about what this number is. By definition, it's the thing that if we have 2 factors of that thing, right? Here's 1 factor, here's 2 factor, and they're being multiplied together, by definition of what a square root is, right? By exactly what that means, it's 335. It's a little bit like saying, if using a ballpoint pen was the thing that made you cry, then what would happen if you used a ballpoint pen? Well, you would cry because we've just defined this ballpoint pen to be the thing that if you use it, it makes you cry. The same thing here, right? The definition of what this square root thing means is it's the thing that if you multiply 2 factors of that thing together, you get 335. You get the radicand back out of that. So if you had, for example, the third root of, I don't know, n times the third root of n, would that be anything useful? Not really. But if we have 3 of those things multiplied together, well, then by definition, that would be exactly n. Okay, so then here's the weird question. N is just a number, right? Let's think of it differently than what we were using it for up there. If I told you that we had the nth root of x, and we were multiplying that by the nth root of x, and we were multiplying that by the nth root of x, dot, 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 and we had a whole bunch of these multiplied together, all right? And I told you that the result of that multiplication was exactly x, right? How many of these radicals, of these nth root of x's, would I have had to have multiplied together to get exactly x? Well, the answer is I would have had to have had exactly n of them, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 n is how many of these I'd have to multiply together to get x. It's kind of a weird thing to hear someone talk about. Here's maybe why it becomes useful. Let's say I'm asking you to find the third root of, I don't know, 56, for example. Let's not do 56. Let's do the third root of 112. All right. Well, 112. Let's see. I know it's not a perfect root, so now I've got this kind of a weird thing happening. If I break this down a little bit, 112 is 2 times 56. There's that number again. 56 is 8 times 7, which is 2 times 4, which is 2 times 2. All right. So then what we're saying here is we've got the cube root, the cube root of 112 is the same thing as the cube root of 2 times the cube root of 2 times the cube root of 2, 1, 2, 3, 4 of those, the cube root of 2 times the cube root of 7. What's going to happen here? Do all of these cube roots of 2 just make 2? Careful. They don't, because I have 1, 2, 3, 4 factors of the cube root of 2. And by definition, if I multiply 3 of these together, that would give me exactly 2. So then over here I have the cube root of 2 times the cube root of 7. Nothing useful is happening in terms of the cube root of 3 times the cube root of 7 being something fancy. So what we can do here is we can just say, well, that's just going to be the cube root of 14. Now if I were to cube this thing, right, if I were taking, so this is the result, right? This is the cube root of 112. If you were to multiply this thing by itself 3 times, right? So if you had 2 root 3 or I'm sorry, 2 times 3, yeah, 2 times the third root of 14 times 2 times the third root of 14 and 2 times the third root of 14. What you'd have here is you'd have 2 times 2 times 2. That's a 3. 2 times 2, which is 2, 4, 8. Right? Cube root of 14 times the cube root of 14 times the cube root of 14. By definition, those three cube roots multiply together to give us 14. And you can check it real quick. 8 times 14 is in fact exactly 112.